I like to just kind of keep practicing what we've been doing. And then I want to show why, it's better to get a delta H and a delta S and solve for delta G than it is to just use the standard Gibbs free energies. So anyway, take a second. I would like you to predict the change in entropy for the reaction of nitrogen and fluorine to make nitrogen trifluoride. And I want you to make a prediction, and then I want you to actually calculate it. So the first thing you actually have to do is write a balanced reaction. So we have to write the balanced equation between nitrogen, N2, and fluorine, F2, to create nitrogen trifluoride. And if you go to balance it, you got 2 nitrogens, so you're going to put a 2 there. That gets us 6 fluorines, and you're going to put a 3 there. So now you should be able to use these standard entropy values. Not going to make you look them up in a table. And you should be able to calculate delta S for that reaction. Go ahead. So I got negative 278.37 joules per mole times Kelvin. Hopefully you predicted that there would be a negative value. Why? We go from 4 gaseous equivalents down to 2. This is becoming more ordered. That's a decrease in entropy. That's a negative delta S. Here I'd like you to try to get delta H for this reaction and delta S for this reaction. And then I want to pause. And then we're going to get delta S at 25 degrees Celsius. Okay? And I'm sorry, we're going to get delta G. I think I said S. And we're going to get delta G at 25 degrees Celsius from our delta H's and delta S's using that beautiful delta G equals delta H minus T times delta S formula. But first, getting way ahead of ourselves, 3-step process here. I'd like you to get me delta H and delta S, and then we'll talk about getting delta G. Go ahead. Okay. Hopefully, here's what you got. Hopefully, you got the change in enthalpy, 57.2. Kilojoules per mole, and hopefully you got the change in entropy as positive 175.8. We're going to calculate delta G here in a moment. This is where I want to hopefully tie together that whole 4 different scenarios thing. What kind of reaction do we have here? Well, we have a reaction with a positive delta H. So we have positive delta H, and we have a reaction with a positive delta S. This is an endothermic reaction with an increase in entropy. And I want to talk about the conditions under which it could be spontaneous. Okay, remember the 4 different possibilities. Reactions that are exothermic and have an increase in entropy, they would be spontaneous all the time. We don't have that. We have endothermic and an increase in entropy. Reactions that are endothermic and a decrease in entropy are never spontaneous. We don't have that. We have endothermic and an increase in entropy. So we must have one of those temperature-dependent ones. Now, if we look at the formula, delta G equals delta H minus T times delta S. In the formula, an increase in entropy, that's good for spontaneity. Endothermic, that's bad for spontaneity. This is only going to be spontaneous at high temperatures. So you're only going to get a negative delta G at high temperatures. Let's first calculate whether or not this is spontaneous under thermodynamic standard temp, which is 25 degrees Celsius. So I'm going to calculate what delta G is at 25 degrees Celsius. So here we go. Delta G minus delta H. So, hang on. Delta G equals delta H, 57.2 kilojoules per mole, minus the temperature. It's got to be in Kelvin. So 25 plus 273, that's 298 Kelvin. So you're going to put 298 Kelvin here for the temperature. And here's where you have to be careful. Because my delta H is in kilojoules per mole. Okay? My S cannot be left in joules per mole. I need to divide that by 1,000. So dividing this by 1,000 gets me 0.1758 kilojoules per mole times Kelvin. And now they'll both be kilojoules per mole. Okay, so please watch out for that. So that's times 0.1758 kilojoules per mole times Kelvin. The Kelvin will cancel out, and we'll be left with kilojoules per mole when we plug this in. So 57.2 minus the quantity 298 times 0.1758. And I get a delta G of positive 4.81 kilojoules per mole. Positive 4.81 kilojoules per mole. We're going to do some more with this here in a second. Okay. But what does this tell us? This tells us this reaction is not spontaneous at room temp. Okay, because I got a delta G of positive 4.81. Since it's positive, non-spontaneous. Here's why I like doing it this way, even though it's way more work. I like doing it this way way more than just solving for delta G from the delta G standard formation values. Here's why. If I had just used the delta G values and I found that this had a positive 4.81 kilojoules per mole, I don't know nearly as much than if I do it the long way. Since I've done it the long way, I know this is endothermic with an increase in entropy. I know it's not spontaneous now, but if I increase the temperature, it will become spontaneous. If you just use the delta G's, you don't get any of that, right? You just know it's not spontaneous at room temp. You don't know anything else. You don't know anything else. So this method just gives you way more information. In fact, we are actually now going to solve for at what temperature it would become spontaneous. So my next question is, obviously, endothermic increase in entropy, high temperatures. How hot does it have to be? So what do? To solve for the temperature at which this would become spontaneous, what we do is we put 0 in for delta G, okay? And then we solve for T, okay? So let's do that. Because if you think about it, when it's 0, that's when you're going from positive to negative delta G, right? That's the transition. So any temperature above that for this one would be spontaneous. Okay, would make it spontaneous. So here we go. We're going to say 0 equals 57.2 kilojoules per mole minus T times 0.1758 kilojoules per mole times Kelvin. We're going to subtract 57.2 from both sides. So negative 57.2 kilojoules per mole equals negative 0.1758 kilojoules per mole times Kelvin times T. Divide both sides by negative 0.1758 kilojoules per mole times Kelvin. The kilojoules per mole cancel out. Kelvin goes to the top. And the temperature above which this reaction would become spontaneous will be, drum roll please, right? Yeah. 325 Kelvin. If you subtract 273.15, that's 52 degrees Celsius. So at about 52 degrees, if you heat this thing up above 52 degrees Celsius, this reaction should become spontaneous for you and happen on its own. Now, I have no idea how fast. I have no idea. No idea. Okay, but it will eventually happen as long as the temperature is maintained above 52 degrees Celsius or 325 Kelvin. Hopefully you can see why I prefer to solve for delta H, solve for delta S, and do this the longer way to get delta G instead of just getting delta G right from that table. Because man, you could never do all this, right? It doesn't give you nearly as much information about the reaction. All right, I would like you to try that whole shebang all over again. Can you do it on your own? I'm going to take the leash off, right? You got this. Solve for delta H, solve for delta S, and then solve for delta G at 25 degrees Celsius. Tell me if it's spontaneous or not. And if the reaction is spontaneous, can it ever not be spontaneous? And if it's not spontaneous, can it ever be made to be spontaneous? You got this. All right, folks, here's what you should have hopefully gotten. You should have found this reaction is endothermic with a decrease in entropy. I got positive 64.6 kilojoules per mole from a delta H, and I got a negative 12.7 joules per mole times Kelvin from a delta S. This is never going to be spontaneous. Doesn't matter what the temperature is. We're going to solve for delta G here in a moment, but there's nothing you could do to this reaction that would make it spontaneous. This can't be done, okay? Because if you think about it, no matter what you do, because temperature is in Kelvin, and it's absolute zero is the limit, you can never make temperature negative. This reaction can never have a negative delta G. It's always going to be positive. So let's solve for it at room temp and see what it is, but it's going to be some positive value. So delta G equals delta H, 64.6 kilojoules per mole, minus the temperature, we're at 25 degrees Celsius, so that's 298 Kelvin, times delta S, but it's got to be in kilojoules, negative 0.0127 kilojoules per mole times Kelvin. And we're going to get delta G here. It's going to be some positive value, I guarantee that. That's a positive 68.4. Whoops. 68.4 kilojoules per mole. Now, if you tried to do that trick we did before with the delta G equals delta H minus T times delta S, and if you plug 0 in for here and solve for the temperature, your temperature value will be some negative number. And again, since Kelvin, the absolute stop sign as far as we know for temperature is 0 Kelvin, you're not going to be able to have a negative temperature. Yep. Okay, so we just did this reaction. We solved for delta G. We found it to be a positive 68.4. We did it the long way, but I like this way because I know so much about it. I want to prove to you that doing it the short way will get you the same answer. So go ahead, same reaction, but now I'm just giving you the Gibbs free energy values. See how close we get to the 68.4. They should be the same. Go ahead. So when we do it that way, I got positive 69 kilojoules per mole. So same number, right? Positive 68.4, positive 69. Doesn't matter how you do it. Again, why would you want to go through all that? If you had just solved for this and got a positive 69, and I said, well, okay, can it ever be spontaneous? Your answer would be, I don't know, right? But since we did it the long way and you knew that it was endothermic with a decrease in entropy, your answer would be, yeah, it can never be spontaneous. Okay, so even though it's more work, big fan of doing it that way, the longer way. That's the best way to do that.